Hello, hello. Good morning, everyone. We're gonna get started with today. I thought today we would do a little bit of a different style of warm up. I thought we would do a little poll instead. So here in our poll here, what I'm just sort of curious about is which of the following thingies, where is it? Do you feel like represents a net force? So we have a few different choices here. So what I want you to do is I want you to pick all that applies. So this is a multiple choice, but like the multiple choice where it's like you can pick as many as you want. So I want you to decide, think about which ones you feel like has a net force. Do you feel like a plane cruising at a constant velocity of 300 meters per second? Do you feel like that has a net force? Do you feel like a Tesla Roadster going 0 to 60 in 1.9 seconds has a net force? Do you think a banana sitting on a calendar has a net force? Do you think that Tom Cruise falling at terminal velocity has a net force? And do you think the Earth rotating around the sun has a net force? So I want you to pick all that apply and see which ones you feel like have a net force. Apologize for that. Um, I believe that
You have to
the
actually launch
Tesla
it.
Roadster, from what I just did a little bit of Googling just now, Elon Musk is planning to like add like space like rocket boosters to the new Tesla Roadster. So apparently it can go 0 to 60 in 1.1 seconds. So that is quite interesting. So this slide is already outdated. And I also had a lot of bananas recently, which is why one of the questions features a banana. So if
You
you
didn't launch
if you
the
like
polling.
bananas as much as I
You
do.
have to click
Um,
polling.
okay, so I want you to answer. I have to launch the poll. Hold on. Okay, so I want you to answer as many of these. Pick as many as that you think apply. Which of these do you feel like has a net force? Um, you okay? So which of these do you feel like has a net force? Our goal today is we have 20 people in class right now. Our goal is, so I'm deciding if we want to shoot for a B or if we want to shoot for an A in terms of our response rate. So we're at 6 out of 21, which is 28%. I think we can shoot for a 90% response rate. I know that's very, very ambitious, but I'm a very ambitious person. That means we need about 19 or 20 people to respond. We have 9 people so far, so thank you for all those for responding. For those of you just joining us, what we are doing is we are looking at, we're trying to determine which of these do we feel like have a net, have, which of the following objects do you think have, it should be have a net force. It's, but it's which of the objects. So is it which has, or is it which of the following object have? Okay, if someone can correct my grammar here, that would be very nice. I'm not sure if it's has a net force or it's supposed to be have a net force. Anyways, so I want you to pick which of the following objects net force thing, and I want you to pick all that apply. So that, again, you can have multiple answers for you. So pick whatever ones you feel
Pretty
like
sure it's which
apply.
of those
Um,
has a net force, because you're talking about like one object at a time. So which of them
you think
has?
it? You think it's has?
Yeah, which of them
Okay, okay.
has a net force?
Um,
Because you're talking
okay, so
like
we're at
individual.
17 out of 27 people responding. So thank you for all those responding. I'm going to be honest with you. What if I said the amount of people who respond here is the grade you get in the class? So if we get a 70% response rate, that means everybody gets a 70. See, if
Guys,
I said
everybody
that,
better
I guarantee you
respond.
we're gonna get 100. See, as soon as I said that, now we're at 85%. So we were at
Everybody
70%
better
just like a second
respond.
ago. Now we're at 85%. So as soon as I said that, everyone decided to. Oh, also, okay. Here's the. Oh, no. Okay, so this is the problem I had last class, or I like didn't show you the actual like slides for some reason, and then nobody said anything for like 15 minutes, and then that was like super awkward. So okay, so now you can see the slides. Another thing that I also realized is that you saw the poll answers initially where people were responding, so now like you were like all like just picking what other people picked. So that's a lot of issues right there. This is the, so as you can tell, I'm very, very, very confident with this. Okay, so we're at 85%, which is pretty good. But I'm gonna give you one more minute. We're gonna let's shoot for a 90% here. I think we need 1 or 2 more people to respond, and then we will move on here. So I like all the answers we have so far. So yeah, like 1 more minute, 30 seconds, 20 seconds, 5 seconds. Can we get 2 more people? 2 more people, 2 more people. Otherwise, everybody is going to end up with this grade because that's how grading works. All right, we'll end it here. Thank you for all the who participated. Okay, we just got another person, 89. Okay, we're now at 89%. Thank you for responding. Okay, so which of these have a net force? So there actually are only 3 of these that have a net force. So the first off, the plane cruising at a constant velocity does not actually have a net force because it has a constant velocity. So if it has a constant velocity, it just means that there is no acceleration. And if there's no acceleration, it just means that there's no net force. So this is where things get very tricky. There are a lot of forces acting on the plane, guaranteed. But there's no net force because it's at a constant velocity. So that is very tricky. One thing you should consider. The Tesla Roadster is different though. The Tesla Roadster is actually physically accelerating. It's starting from 0 miles an hour to 60 miles an hour. And so because it's accelerating, it does have a net force. So that is the first one that does. The banana sitting on the counter. So the banana sitting on counter, again, it's sort of like the plane, except it's even more like apparent. The banana is not going anywhere. So the banana has no net force. So so the plane that does have air resistance for the plane and the Tesla both have air resistance. However, it's like you have the lift force pushing the plane forward, and then you have the air resistance pushing the plane back, and they cancel out. So that way the plane has a constant velocity of 300 meters per second. So if there was no air resistance force, right, the plane would probably keep accelerating, and then it would probably have a net force. But the air resistance actually serves, I think, to actually balance out the plane engine force, and that sort of creates no net force, no acceleration. The Tesla, on the other hand, the air resistance force is smaller than the force of the engine, and so because of this, the Tesla is accelerating, and because there is a net force. But the banana sitting on the counter, it's not accelerating, it's not even moving, so there definitely is not a net force here, even though there are forces acting on the banana. Tom Cruise falling at terminal velocity actually does not have a negative velocity again. The air resistance force at terminal velocity, this is when you're falling so fast that you're no longer speeding up. And that's because your air resistance force is just as strong as your force of gravity. So you're not actually speeding up anymore. So your net force is actually 0. And the Earth rotating around the sun, this actually does have a net force. And that's because the net force is the sun pulling the Earth into the sun. So that is sort of the gist of this. Thank you all for those who participated. We did hit our 90% response rate, so that means everyone should be very happy with how things are going. Okay. So what we're going to do today is we're going to talk about our agenda. So what we're going to do is we're going to pretty much talk about free body. Oh, no. This is the wrong. Oh, no. Here's the agenda. Yes, correct. Here we go. No, here we go. Okay. So okay, so here's the agenda. We're going to talk about F equals MA, FEMA, and we're talking about free body diagrams today. So to start this off, there is a graphic organizer on Canvas that I want you to open and submit by the end of the period, similar to last time. There should be a space in there for your warm-up question, but I want you to fill it out and submit it on Canvas by the end of the day. So fill that out. So we're going to do a little bit of introduction to that, and then we'll start on some assignments afterwards, and I'll talk about your due dates. In terms of due dates, I want you to submit the free body diagram practice problems and the force data analysis by Sunday, Monday. We will start the free body practice today. So that's what we're doing today, but I'm going to try to blitz through this agenda. Okay. So once you have your thingamabob open, your graphic organizer, this is the first thing we're going to talk about. So the first thing we're going to talk about is the misconception, the difference between weight and mass. So, oh yeah, something keeps disappearing. It is disappearing again. The difference between free body diagram is the difference between weight and mass. So we like to we commonly sort of interchange the two, but the two are actually not the same thing. So mass is the thing we use in physics and in science. And this is because mass is physically how much stuff an object has. And this does not change where you are or depending on what forces are acting on it. And this is what kilograms is. Kilograms is a measure of mass. And it just means that if I have 10 kilograms of something, it means that I have 10 kilograms worth of stuff. Excuse me. And that 10 kilograms of stuff never changes depending on where you are. However, weight, on the other hand, is a measurement of the force of gravity. So when I gave you the data set last Tuesday, whatever, that data set was measuring the force of gravity on a weight, and that is that is what the measurement of weight is. And so when you measure your weight in pounds, right, you're really just measuring the force of gravity acting upon you. And so how much you weigh or an object weighs depends on its mass, right? How much stuff you have, but also the acceleration due to gravity, depending what the object is. So this means that objects that if you are in a location with a smaller force of gravity, you will weigh less. Whereas in your location with a bigger force of gravity, that means you will weigh more. So this is why you weigh 6 times less on the moon than you do on Earth. So in terms of units, how we measure things, so when we measure the mass of stuff, we use kilograms. However, when we measure the weight of things, we use, would a kilogram scale be the same on the moon and on Earth? So the way I think kilograms scale works, I'm pretty sure how kilograms scale work is that they measure the weight of an object and then they divide it by the force of gravity to get your mass. So I don't think a kilogram scale would be the same on moon on Earth. I think you would have to calibrate the kilogram scale to work on the moon. That's because it's very hard to like physically just measure the mass of an object. It's much easier to measure the weight of it and then convert it to kilograms, which is kind of ironic. But I think that actually is actually a lot easier than trying to measure the mass straight up. So that's because of that. I think you would have to recalibrate the kilogram scale to work on the moon. So because of this, kilogram scales, again, they measure mass. If you want to measure the weight of an object, right, if you want to measure the force of gravity, we can use Newton's second law, F equals ma. So in this case, we're trying to figure out the force of gravity, which is Fg. So Fg is equal to the mass times the acceleration due to gravity, which in this case, the mass is 1, the acceleration due to gravity is 10. And so in this example here, the force of gravity is 10 kilograms meter per second squared. So we would actually say that this object actually weighs 10 newtons. So Newton in this case is a measurement of the force of gravity. So to quickly recap this, when we look at the weight of an object, we're looking at the strength of the force of gravity acting on it. And when doing so, we use Newton's second law to figure out the force of gravity. And what this means is that we actually found the units that we measure force in, units we found measure force in, the units we measure weight in, and that is a Newton. N for Newton, 1 Newton is 1 kilograms times meters per second squared. So if you look at the units here, you'll notice that the units for force is the units for mass, which is kilograms, times units for acceleration, which is meters per second squared. So when you combine them, you get meter kilograms times meters per second squared. It's very helpful. I mean, you 100% will need to know the units, newtons. I would highly recommend to also understand what a Newton is in terms of kilograms and meters per second squared, because that'll help you sort of understand if you're sort of getting the right answer or not, because you'll understand how your units are mixing. So know your units, it's newtons. 1 Newton is kilograms times meter per second squared. And the weight of an object is the same as the force of gravity. Okay, so the force of gravity. So I think a common misconception that I want to clarify now is that gravity is a physical force. Gravity causes an object to accelerate. Gravity itself is not acceleration. Gravity is a force that causes acceleration. And the strength of the force of gravity depends only on the mass of an object. Only on the mass. So what this means is that an object accelerating towards the Earth has a constant acceleration that doesn't depend on the mass. So what this means is that, right, when you look at the gravitational acceleration constant, right, that's 9.8 meters per second squared. That's the same for any object on Earth. Any object on Earth, and the strength of the force does change. But if you have a bigger force and a bigger mass, right, so they sort of cancel out. So you get the same acceleration on Earth due to gravity from all things, which is g, which is 9.8 meters per second squared. So what I want you to do now is to, once you sort of run things, is it just me or do things just keep disappearing? Um, hold on, hold on. Okay, here we go. Apologize, my apologies, my apologies. If I do something, it does something, and it does something, it breaks something. Okay, so here is what we are going to do now is we are going to quickly figure out the force of gravity on a coin and a feather. Okay, yeah. So I'm supposed to be observed today, but I think my observer was not able to make it, which is why I'm a little like all over the place. I'm sort of checking to see if he's here, but he just emailed me saying he's not going to be able to make it. So because of this, I'm a little flustered. But that's okay. So what I want you to do now is I want you to figure out the force of gravity on coin and a feather. So the force of gravity. So in this case, the mass of the coin is the mass of a coin is 12 kilograms. So I read this and I'm like, what the hell? Yeah. So the mass of a coin is 12 kilograms here apparently, and then the mass of a feather is 0.012 kilogram. So oh, thank you. I appreciate it, John. Yeah, I know that. I know you're gonna do that. Fortunately, he's not here, so you can't. So there's no need to be super excited. No, physics is fun. So who doesn't love being excited? Okay, so sorry, I'm being distracted. Okay, so the mass of the coin is 12 kilograms. The mass of the feather is 0.012 kilograms. So our goal here is we want to figure out the force of gravity and the weight on both of these, and to sort of talk about which one hits the ground first. So I'm going to give you a couple of minutes to try to figure this out. Whenever you're ready, just put your answers in the Zoom chat. So to figure out the force of gravity, right, you're going to want to use the Newton's second law, F equals ma. So in this case, our F is the force of gravity, and the acceleration is going to be the acceleration due to gravity, which is 9.8 meters per second squared. So do that real quick, and then see if we can figure out the force of gravity and the weight on both of these objects, and then talk about which of these you think will hit the ground first. Once again, if I'm going to give you to sort of figure out the force, right, we can use Newton's second law, which is that the force of an object is equal to its mass times its acceleration. So if we want to figure out the force of gravity, right, we want to use the mass of the object, and we're going to want to multiply it by the acceleration due to gravity, which is g, which is 9.8 meters per second squared. So we can use that to figure out the force of gravity, and then the weight of the coin, and then the force of gravity on the feather, and the weight of the feather. And then you can talk about which one you think hits the ground first. So whenever you're ready, you can just put your answers in the Zoom chat, just so I know we're ready to move on here.
What unit would the force be? Would it be in newtons? Mr. Who?
Okay, so to figure out the force of gravity on the coin, we can take the mass of the coin, which is 12 kilograms, and we can multiply it by the acceleration to gravity, which is 9.8. So if we take 12 and we multiply it by 9.8, we'll get something like 117.6. So that'll be the force newtons. So that'll be the force of gravity on the coin, which will be the same as the weight of the coin, because the force of gravity and the weight of the coin are the same thing. For the feather, we will do the same thing. So how do you find the weight in newtons? So if you take the mass of an object and you multiply by acceleration, so as long as your mass is in kilograms and as long as your acceleration is in meters per second squared, when you multiply them, you will magically get newtons. So that's why it's so important to have your units set up properly, because they'll convert to each other perfectly. So if you set up your equation as in force is equal to mass times acceleration, if you want to find your force measured in newtons, you want to make sure your mass is measured in kilograms and your acceleration is measured in meters per second squared. Then when you multiply your kilograms with your acceleration, your meters per second squared, they will turn into kilograms times meters per second squared, which is newtons. So you don't have to do any conversion as long as you set up everything properly. So in this case, I already gave you your masses in kilograms and your acceleration of gravity is already in 9.8 meters per second squared. So when you take your mass, let's say the mass of the feather, which is 0.012 kilograms, and you multiply it by 9.8, your answer will be something like 0.176, but you don't have to convert it to anything because that's already in newtons. So the force and weight in newtons are the same. Exactly. Force and weight in newtons are exactly the same. They mean the same thing. It's almost like this is almost a trick question, but it's not, because the force of gravity and the weight are the same thing. They're the same thing. So because of this, the force of gravity should be it should be 176, I think, for the coin, and like 0.176 or something like that, 1176 or something for the feather. And which one hits the bottom first? So they both will hit the bottom at the exact same time, and this is because the acceleration due to gravity is the same. I know some of you are going to say air resistance, whatever. Yes, but this is physics, and in physics, we don't care about stuff like air resistance because that's too much work. So they will hit the ground at the exact same time because they both accelerate at the same rate.
But so, how do we find the weight
to sort of quickly
newtons?
just give you the gist of it, right? An object accelerates when there is a net force on an object. This is very important, the word net force. So what does it mean to have a net force? So acceleration causes net force, and acceleration is when your velocity changes. What does it mean to have a net force? A net force is when your forces are now balanced out. So I think a better way of saying Newton's second law, so when we say Newton's second law, we always say F is equal to ma, which it really should say is your net force is equal to your mass, your overall mass times your overall acceleration. So because we want to be looking at the net force, right? I'm not understanding. Okay, so how do you find the weight in newtons? Okay, so okay, let's see. I'll actually let's do the feather problem again. I think I might have. Okay, so what we want to do is we actually want to figure out the force of gravity on the coin. So that we have the mass and we have the acceleration. So the mass I already gave to you. This is 12, and then this is 0.012. What is the acceleration? Well, the acceleration of a falling coin and a falling feather, they are both g. Right? Because all objects accelerate the exact same rate, and these are both 9.8 meters per second squared. So if I want to figure out the force of gravity, what I want to say is the force of gravity, Fg. I'm going to use this notation a lot. So, and I will talk about this a bit more. This is the force of gravity. This is just a notation you use. Force of gravity. The force of gravity on the object is the same as the weight. They mean the same thing. And this is equal to the mass of an object times its acceleration. Right. So this is Newton's. In general, Newton's second law is F equals ma. The net force of an object is equal to the mass times acceleration. So if I want to figure out the force of gravity, I just need to find have the mass and the acceleration. And so in this case, we already know our acceleration, which is g. So I can just plug this in here, and this is our force of gravity will then equal mass times gravity. So what I'm going to do here is I'm going to multiply our mass by my gravity. So this is going to be for the coin. This is going to be 12 times 9.8. Actually, I'll include the units here so you can actually see what happens. So our mass here is in kilograms, and our acceleration is in 9.8 meters per second squared. And this will be our force of gravity. So when I multiply this out, I get 117, I think, 0.6 kilograms times meters per second squared. So this is what your answer should look like, something like this, right? I think this part should be understandable. Now the thing is, a kilogram meters per second squared, 1 Newton, is equal to 1 kilogram times meters per second squared. It's just not like a conversion, right? So this 1 Newton is just 1 kilograms times meters per second squared. And as you notice here, when we set it up, we already had our mass in terms of kilograms. We already had our acceleration in terms of meters per second squared. So our answer is going to be kilograms per meters per second squared. And guess what? This is just the same thing as the Newton. Bam. So that's it. There's nothing really special about the Newton. You don't really have to worry so much about finding the weight in Newtons. As long as your mass is in kilograms and your acceleration is in meters per second squared, you're just automatically just going to get your answer in Newtons. So the key here, if you don't want to have to worry about this whole unit shebang thing, it's more important to just focus on, I want my mass in kilograms always in physics. I want my acceleration in meters per second squared, always in physics. And then your answer will just magically turn into a Newton. If you don't care about magic, if you're like magic doesn't exist, you'll understand here that a Newton is 1 kilogram per meter squared. So I have this kilogram per meter second squared. I can just turn this into a Newton. Does that make sense? Hopefully I did a better job of explaining it this time.
It makes some sense, but we still have a kilogram. So, oh, I see. Yeah, you remove
Okay.
kilogram.
Okay. Okay. Hey, let me know if that still doesn't make sense, and I'll try to explain it some more. Hopefully that helps a little bit. Okay. So what we want to do here is we want to look at the net force of an object because this is very important. So the net force of an object is basically what happens after we do all our balancing forces and stuff, right? So forces can act in a bunch of different directions, which means that I can't hear you when you talk. That might actually be a. Oh no. Okay, can you guys say something right now?
Yeah.
Okay, now I can hear you. Okay. Okay, so that that explains a lot. Okay, all right. Okay, so now that we can actually communicate, okay, so now you can lay it on to me what I did wrong. So okay, so what do you want me to go over? I think I probably messed up a lot of things. So did this make sense more? Is this better, preferable?
Yeah, it made more sense.
Yeah, it made more sense.
Okay. There we go. Okay. I'm glad we can actually communicate now. I wasn't ignoring you. I just literally couldn't hear you. So I think I messed something up. Okay. So we're on the same page. We're okay here. Okay. We can move on.
Yeah.
Okay. Yes. So as you can tell, I'm perfect. I never make any mistakes. Okay. So
Never.
let's talk a little bit about balanced forces here. So we want to figure out our net force, which means that we want to figure out how our forces all balance out and stuff. So in this example here, what we have is two groups of people playing tug of rope. And so in the first example, we have one group pulling to the left with a force of 300 newtons. And then we have a group pulling to the right with a force of 300 newtons. Well, if one group is pulling to the left with 300 and the other group is pulling to the right with 300, guess what? They sort of balance out, right? They're pulling with the exact same force. So there's no net force. So nobody's going to accelerate. And if you think about this, right, I think about physically what happens when you play tug of rope, if you have two evenly matched groups of people pulling with the same force, right, nobody's going to move. And so this means our net force in this example is going to be 0. And our acceleration is going to be 0. If you think about it, right, you can think about it as I have one force that is negative 300 and I have one force that is positive 300. And so when you add them together, they sort of cancel out. And so you have a net force of 0. In the second example here, the left group, they started lifting, they got much swoller, and so now they're putting out 400 newtons of force instead of 300. So now, as you can tell, the left group is pulling with a lot more force than the right group. So if you were to look at it, right, I've got one group pulling to the left with 400, one group pulling to the right with 300. So the net force is going to be like 100 to the left, right? You can think about it, I'm subtracting 300 from 400, and so I'm going to have a net force of 100. And so the net force in this example is not going to be equal to 0, and our acceleration is not going to be equal to 0. So the overall system, the overall group of people is going to accelerate to the left. So let's examine this a little bit more. So let's actually physically see what happens here. So in this example, I have three masses, well, three things. They all have the same mass of 10 kilograms, but they all have the net forces are of different strengths and of different directions. So I have four different boxes here. In the first example, right, I have a mass of 10 kilograms. It's being pulled to the right with a force of 5, and it's being pulled to the right with a force of 10. So the net force is going to be a force of 15 to the right. Right? That sort of makes sense. The second example, I'm pulling to the left with 5, and I'm pulling to the right with 10. And so your net force is going to be 5 to the right. You sort of subtract them. So what I want you to do is I want you to figure out the mass, the net force of the third one. And then I want you to figure out the acceleration of all three of these examples. So the third example, you're pulling to the left with 5, pulling to the right with 5. So what would our net force be? And then let's figure out our accelerations. So for each example. So again, the key formula you want to use here is F net is equal to ma. Your net force is equal to your mass times acceleration. So
There's like four little pieces for the 4 columns for the table. Do we
there are
have to do
four columns.
or rows or whatever? Like
There's 4 rows. It's supposed
yeah,
to be
4
3
rows.
rows.
Sorry.
That was okay. Hold on.
We can just delete
When
the
the last
poem.
time I checked it, when I wrote it, it was not supposed to be like that. I probably, as you can tell. Oh yeah. Oh, I see what you mean. I think I added an extra row in accident. Hold
So
on.
we can just delete that row.
Yeah.
Nice.
Yeah. Don't worry, guys. Don't worry. I'm. It was intentional. It was just to see if you guys are paying attention. I feel like I just lost so much respect from you guys. Not that I had any to begin with, but I feel like it really is. I feel like at this point it's like negative, like respect. It's like we don't respect you at all, which is okay. But I think it's funny. I can just hear the disappointment, even though you're not saying anything. Usually you would say like, oh, Mr. Who, like we don't, it's fine. But like because I can't, all I hear is a deafening silence. So I
Mr.
just, like,
Who, it's
know.
fine. Don't worry. You're still the
Yeah,
king.
don't worry about it, bro.
You're fine.
Oh, it's okay. I suffer from inferiority complex, so okay. I'm doing my best. Okay, so hopefully, so now that we resolved the 4-row crisis that we had, hopefully you were able to figure out the net forces. I think I'm going to just quickly show you how to do this. So the last net force is going to be 0 because you're pulling to the left with 5, pulling to the right with 5, so your net force is 0. So in terms of your accelerations, you have a net force of 15 for the first one, and you have a mass of 10. So you have F equals ma, 15 is equal to 10 times acceleration. So your acceleration is going to be 1.5 for the first one. It's going to be 0.5 for the second one, and then it's going to be 0 for the last one. So again, you just set your net force is equal to your mass times acceleration, and then you should be able to work it out reasonably. So sort of a quickly recap, right? If I want to have a net force of 0, so if this girl, if she's holding a thingy-mabob and she wants to keep it steady, the Earth is pulling it down with the force of gravity. So in order to keep it steady, the girl has to pull up with the same amount of force as gravity in order to give it a net force of 0. Okay, so on this table here, so this is a physics book. this is sort of similar. This is exactly similar to the banana example earlier. So this banana is sitting on a level table, and let's identify all the forces acting on it. So
Wait, I have a quick question,
go ahead, please, go
which
ahead.
is that for like the whole like acceleration, like find acceleration, magnitude, and direction for the block. I'm a little unclear on like exactly how to do it. Like I think I did it right, but
Okay. I'll do it on the board. Okay.
just so, like, just one, just so I can.
Okay. I agree. That's very helpful. Okay, so okay, so okay, let's do the first one. Okay, so the first one here, I point to the right with 5, I point to the right with 10. So my net force, F net, is equal to 15 newtons. Now, for the general equation for finding mass times acceleration is F net is equal to mass times acceleration. So if I have 15 newtons of net force, this is going to be equal to my mass times my acceleration. My mass for the example was 10 kilograms. So if I just quickly do this, 15 newtons is equal to 10 times acceleration. So I got my acceleration should be 1.5 meters per second squared. So once again, because I left my units for forces newtons, I left my mass in terms of kilograms, my acceleration is automatically going to be in meters per second squared. I don't really have to do this any messy conversion. If you wanted to sort of see how you can actually do it without like sort of just, if you don't trust the system, you don't trust the system, I can write the newtons in terms of 15 kilograms meters per second squared. If I can do this, and this is equal to 10 times kilograms times acceleration. So if you were to actually work this out, you can cancel out your kilograms. So your answer will be 1.5 meters per second squared. So this is just sort of to show you, you'll get the same thing either way. This is if you don't trust the system. This is if you trust the system. So there's multiple options for all of you on how much you trust the system. Does that help in terms of how to quickly do this? We will do a little bit more. Yeah, we will do more of this, but this is honestly, this is pretty much like what you need to know. The hardest part is not the MA part. The hardest part is going to be to figure out your net force, and you'll see why it can be very hard to figure out the net force. So hopefully we're able to feel comfortable with this. We're going to be talking a lot more about how to find the net force right now. Okay, so let's talk about how to identify the net force of an object. So this banana on a table, it's sitting on a level table. So let's identify what all the forces are acting on it. An example is a physics book. I like to for bananas. So this is that's probably not let's just use a book instead, or let's just say for like reasons. Okay, so this physics book. Okay. So what are the example of the forces acting on it? Okay, so if I'm a book on a table, right, gravity's pulling me down. What's another force acting on me? Well, gravity's pulling me down. I'm also sort of being pushed up by the table. Right? Because the table is putting in force to keep me from falling. It's like a chair, right? If you're sitting on a chair, right, you can feel the chair pushing up on you. And so you'll see that, okay, I have two forces acting on me. I have the force of gravity pulling me down, and I have the force of the table pulling me up. And so the net force here, my F net here, is going to be 0 because if I leave a book on the table, right, it's not going to accelerate. So that means my net force is 0, and that means my acceleration is 0. So when you think about an object, you want to identify, is my object accelerating? Is it accelerating? If it's not accelerating, your net force should be 0. And so so when you visualize it, you should look at all the arrows and stuff, and they should all cancel out. So I know that my force of gravity exists, which means that I have to have some sort of upward force pushing up on it in order to establish a net force of 0. So I have this gravity force, gravity. I'm going to call this G. This is the notation of forces is going to be very important. But in general, your notation is going to be capital F, and then the little subscript is going to be the name of the force. So in this example, it's going to be gravity, but you'll see that we have other kinds of forces as well. So yeah, so this is just a quick visual idea of what forces are acting on a book. Let's identify what this table force is called. So the table force is what we call a normal force. So a normal force is how much is the force that an object has from a support force. It's like if I'm sitting on an object, right? The object is supporting me. So this support force is perpendicular to the surface. So a table, if I put a book on a table, the support force, the normal force, is going to be perpendicular to the surface of the table. If the object is not accelerating, does that mean the net force is 0? Yes. If the object is not accelerating, it means the net force is 0. When we measure weight in kilograms, is the unit actually kilograms meters per second squared? Otherwise, it would not make sense for kilograms to mean two different things. So when we measure weight in kilograms, it's not actually like we're not actually measuring your weight. You're actually measuring your mass. It's just like this is why it's really confusing. So when you measure your weight in kilograms, you're really actually measuring your mass. People just use them interchangeably when they really shouldn't. So when you're measuring your weight, you actually should be measuring it in pounds or newtons. When you're measuring your mass, you're measuring in kilograms. So if you sit on a kilogram scale, that's actually measuring your mass. It's not actually measuring your weight. So that's a very key nuance. You're actually measuring, you are measuring your mass. You're not measuring your weight. And again, if the object is not accelerating, your net force is 0. So in this example here, in terms of the normal force, the normal force is probably one of the hardest forces to understand because it's really wonky. It's basically, it's really just the surface of an object is applying a force to the object on it, and it's perpendicular to the surface itself. So on a book, on a table, right, the book is being supported upwards. So the normal force is perpendicular to the surface of the table, so it's upwards. This ramp here, the normal force is perpendicular to the ramp. It's not vertically up. It's actually perpendicular to the ramp, so it's going to be at an angle. And then the girl resting her back on a wall, the wall is going to apply a perpendicular force to the wall, so it's going to be coming in like this. Normal force is probably one of the hardest ones to grasp, and it can get really wonky. This is the general idea is that it's perpendicular to the surface, and then it's a support force. So when we use forces, forces is probably one of the most visual units in physics, which I think is good because it means you can understand it the most. So the best way to visualize all of these things is to do what we call a free body diagram. So these are extremely important because literally for every single problem you do in physics, you will probably have to draw a free body diagram. I will probably ask you to, or it's just smart to do that. And a free body diagram is a diagram that you use to draw all of the forces acting on an object. So when you draw a free body diagram, you list all of the forces acting on it. You're going to draw an arrow, and you're going to draw an arrow pointing in the direction of the force, and how long that arrow is the magnitude of the arrow. So each force you have is going to be labeled with a symbol, and you're going to draw every object as a box, and you're going to draw the force the force arrow outward from the box. So what I'm going to do now is I'm going to draw a free body diagram for the first example. If you look on your graphic organizer, on the very bottom, there should be an example for the first free body diagram. So what I'm going to do is let's draw a free body diagram for this. So the first thing you want to do is let's draw the object itself. So the object itself is a box. It's not a book, it's a box. Every object is a box in physics. Let's draw we have our object. Now we need to draw some forces. Well, the thing we want to do is let's first identify which forces are acting on it. We know the force of gravity always exists on an object. So we know there's a force of gravity here. We want to label it with an FG. We want to draw the arrow starting from the box and going outwards. We don't want to draw it like this. And we don't actually want to draw it from the box going outwards. The force of gravity is pointing downwards. So we're going to have the force of gravity at G. We're also going to have a force pointing upwards from the table, as we described earlier. We're going to have a normal force from the table, and so we want to try and okay. Now, another thing that's important is that the size does matter here. The length does matter here because the size length the dimensions of the arrow all refer to the strength of the force. And so if I draw my force of gravity like this, right, this means that my force of gravity is like a billion times bigger than my normal force, which means that I will actually be accelerating downwards in this example, because my force of gravity is so much bigger than my normal force. But in this example, we're not actually doing this. We actually have a net force of 0. So my arrows, the force arrows, should actually look the same, look like they have the same strength, same size. So this is BuzzFeed's article for physics. Here are your 3 must-know hacks for physics, life hacks for physics. First off, every object you draw is a box. I don't want to see some beautiful car or 3-dimensional like CAD, like diagram stuff. I don't want to see that. I want to see a box. Everything is a box. A circle is a box. A triangle is a box. An earth is a box. Everything is a box. Then I want you to identify the net force of the problem. This is where you think, is my object accelerating in a direction? If it's not accelerating in a direction, my net force is 0, which means that all of my arrows must cancel out. The length of the arrows do matter because they tell us how strong the force is in that direction. If there is a net force, it means that one of the arrows is not going to be balanced out, either there's no forces canceling it out, or the force is just much stronger than the force is trying to cancel it out. The last hack you should know is that just because an object is not moving, or if it's not accelerating, or if it's accelerating in a direction, it doesn't mean if it isn't moving or it's not accelerating in a direction, it doesn't mean that there's forces in the diagram. So let's say if an object is, if I have a book on a table, right, it's not moving and it's not accelerating, it doesn't mean that there's no forces on it. It just means that there's no net force, right? Because gravity always exists on an object. So by definition, you should always have a force acting on an object, which means that you need to have, you should consider how your forces are acting. Another thing that I will reiterate 100 times is that just because an object is moving does not mean that there is a force on it. Force means that something is pushing or pulling in it. If when you throw an object, after you throw it, right, there's no force pushing it forward anymore. There might be a force pushing it backwards because of air resistance, but after you throw the ball, there's no more force pushing it forward. I guarantee you'll see a problem like this, and I guarantee you're gonna be like, okay, there's a force pushing it forwards, but there's not a force pushing it forwards because you already threw it. So what we're gonna do for the next 3 minutes or so is I'm gonna start going over the rest of the forces that you should know. Friction is probably is also a very nasty force. In general, friction is just a force that opposes your motion. So when you slide an object forward, friction is a force that slides against it, that pushes it backwards. Friction is a force that is a contact force. So if you are not in contact with the object, with another object, so if I'm just like a plane, planes don't really have to deal with friction because planes are not on the ground. So friction is a force that opposes other motion. And so if I push an object forward, friction pushes it backwards, and you label it F. Big F and then little f. And so that's just a force that opposes motion. Air resistance is like sort of like a special frictional force that only applies it's a force that resists motion due to air. So generally objects that are flying have air resistance. Honestly, like even every object that moves has air resistance. Most of the time we will say that we live in a magical world that doesn't have air resistance because it can get pretty complicated, but just conceptually it's the air force. It's a force of air that tends to resist the motion of an object. So that's more or less what you need to know about air resistance.
How do we name a force that someone intentionally gives to an object, like pushing?
That's okay. So the force that you apply to an object, to push an object, is called the force, the applied force, or FAP. I'll show you the exact diagram. But yes, we call it an applied force, and so we would label it FAPP. Yeah, so that's the applied force that you are physically putting, that an engine is putting. It means that someone has to put that force in, and that's very. I would always do the applied force last when you're drawing a free body diagram, because that one is the one that can be one of the hardest to identify. Oh, another one that's hard to identify. Tension is brutal. Tension is brutal. Tension is so hard to work with. So in general, anytime you have a string, a rope, a cable, or a wire, you have tension. And tension is basically like it's a force of the cable or whatever that's because it's being stretched, it's applying a force that sort of resists the change. An example here, you have a sugar packet that's being pulled downwards by gravity. And so you have a tension force of the rope that's pulling it upwards. That it generally tends to resist the motion, but that's, it's not always necessarily truth. It's like a pulling force that's due to the string, rope, cable, or wire stretching. So in general, when things are connected, there is some sort of tension force. String, ropes, and cables and wires are dead giveaways. If you have wording that says any of these, you have a tension force. Sometimes if you have well, you probably will see a problem with like trains, and trains are connected together. There's also a tension force there. So tension forces are brutal, or they are absolutely brutal. They're really hard to figure out. But in general, in terms of identifying it, if you have a string, rope, cable, or wire, you have a tension force, guaranteed. How much that tension force is going to be brutal. We will spend a lot of time trying to figure out the exact nuances. But for now, I just want you to know string, rope, cable, wire, tension. Tension. It's very easy to get this confused with an applied force. If an object is being pulled down and with the rope on top, it's a tension force. It's not an applied force. Very, very nasty.
I have a quick question then. Would the motionless backpack suspended by one strap, would that be an example of tension force since it's like one strap, which is like fabric, rope, cable?
Okay. So let's go to that one actually right now. Okay, so let's actually visualize. I have a backpack right here. So I have a backpack right here. So let's identify the forces on it. So this backpack is being pulled down by gravity. So let's call this backpack. This backpack is being pulled down by gravity.
It show your slides, not your.
Not me. Okay? Yes. Here you go. Now you can see me. Okay. So I have a backpack here. Right. You can see it's being pulled down by gravity. So I have a force of gravity pulling it down. It's not accelerating, and there's not really anything pulling it left or right. So that means there's not really anything left or right. We know there has to be a force pulling it up. Now this one is kind of hard to. There's a lot of different things here. So what is keeping my backpack up? What's keeping it up is the fact that my shoulder is pushing it up, right? There's anything else here is just junk. It's just not really. It's just kind of like pointing. What's keeping it up is my shoulder pulling it up. So on my backpack here, you're really just looking at your strap, and then what's keeping it up is my shoulder coming into contact with it, which is giving it a normal force. So the backpack being pulled down by gravity, then I have a shoulder pulling it up. There can be a lot of shenanigans with like the shoulder strap being like tension because it's stretchy and stuff. We're not going to go into that much depth just because it's very nasty. But we really just want to visualize this as my shoulder is keeping my strap up, and that's a normal force for sure. And gravity's coming down. We can get into nuances with tension, like just stretching, whatever. But that's probably not really. It's going to be kind of nasty to deal with. So it's better just to visualize it as just my shoulders keeping it up. And so that's it. So to quickly recap what are the forces that you should know. You should know a tension force, which is Ft. You should know your applied force, your pushing force, which is what Sokei was saying, FAP. You know your force of gravity, Fg, your friction force, Ff, your fair, and then your Fn, which is your normal force. So these are 100% things you should know, the notation. When you drive free body diagrams, you'll be doing this a lot. So an acorn falling from a tree. This is another one that's going to be very tricky. So an acorn falling from a tree, there's just one force, and it's the force of gravity. That's it. In this problem, we said to neglect air resistance. So there's only one force acting on it. It's just the force of gravity. The backpack I just did is the normal force keeping it up. And then a book being pushed to the right. So a book being pushed to the right. So it's being pushed to the right with an acceleration. So we need to have some sort of applied force Now we said in this problem to consider frictional forces. So if I'm pushing it to the right, I'm going to consider the frictional force opposing to the left. Notice how the frictional force is much smaller than my applied force. Okay, so you might think, okay, we're done. That's it. All right. Have a nice day. Not true. More forces. There are more forces here. Remember, the force of gravity always exists. Pretty sure the force of gravity. And then because a book is going to be on a table or desk or whatever, you're going to have to apply your normal force. So remember, you want to consider all the different possible dimensions, the different directions that your forces can apply on before you call it a day. So this is more or less the gist of it, the gist of forces, a free body diagram. In terms of actually drawing it, it's not that hard. The hardest part is going to be understanding which forces are on or are in the system, which forces are being applied, where is what and what is what. So you will have a lot of practice with that today, and for this assignment. So the assignment we're going to be working on today is on Canvas. It's called free body diagram practice problems. I'm going to link it in the chat here, so you should be able to see it. So we're going to try to get through as many as we can today. So there is a little like interactive that you can do if you want. I'm going to make it optional because due to timing, I don't want to kill you guys with work. So I'm going to make it optional. However, it can be very helpful to do if you want to like try it out, and you will get, it'll say if you're doing it correctly or not. So if you want some immediate positive feedback, because I don't like to do that. So if you want some immediate positive feedback, you can do the interactive for a little bit of extra practice. Otherwise, you can jump straight into the actual drawing ones. The actual drawing ones are actually fairly challenging. So it's really up to you which one you want to start with. I'm only asking you to do part 2. Part 1 is if you just want extra practice. Part 2, you're just going to be drawing free body diagrams for all of these situations. The hardest thing is not going to be necessarily drawing it. It's going to be just thinking about which forces are there and which forces, more importantly, which forces aren't there. That's another good thing to consider. So I'm going to, for the rest of the day, since we only have about 13 minutes, I'm just going to let you work on it and get as much progress as you can. And I'll, of course, answer any questions. If you feel like I butchered any part of the lesson or feel like you want me to go anything over, just let me know and I will try to answer it. Otherwise, I'll just let you get working on it. And then, yeah, let me know if you have any questions.
Mr. Hu, could you go back to the slide with the girl trying to hold up the rock? I think
Oh,
I
yeah.
missed that.
Yeah, so with the slide, the girl holding the rock, if she wants to keep the rock steady, the earth is pulling the rock down. So if she wants to get the rock steady, she needs to hold it with an upward force that's equal to the force of gravity. This is very much identical to the backpack problem, where if you want to keep the backpack steady, the normal force needs to be the same as the force down. So in this case, the girl is actually applying. So the rock has a normal force from the girl's hands that is keeping it upwards, and then it has the force of gravity pulling it downwards.
All right, thanks.
Okay, so we got 1 minute left. So here's what my expectations are. Okay, so the force data analysis that we did on Tuesday, I want you to have sort of a rough draft. You know, it doesn't need to be perfect. We're gonna spend a good amount of time revising it, and you know, it's gonna be me giving you feedback. You're gonna do some self-assessment. So it does not need to be perfect. Just try to have a good thing done. The free body diagram practice problems. So these are not graded. These are just for practice. That's why they're called practice problems. So I want you to try to finish them by next Monday. I do not care if they are correct or not. I will give you feedback, and I will try to actually I'll be helpful-ish on them. So try to do the best you can. If you don't know how to do it, give it your best guess, and then I'll give you feedback on what what some things that you can look at or try to revise and stuff. So it's it's not graded. So don't stress out too much about it. The practice problems should not take you more than don't spend more than like 10-20 minutes on them. Just try to hammer them out. If you aren't sure, give it your best guess and then move on. It's not the end of the world. And so that's sort of my expectations. So hopefully the workload itself is going to be reasonable. Nothing crazy, but again, let me know if it is. Other than that, I will see you all next Tuesday, where we will do a lot more forces and stuff. So this is going to be a very content heavy curriculum. Oh, sorry. Next class is on Wednesday. Yes. Our next class is on Wednesday because it's Martin Luther King. So I'll see you guys next Wednesday. That means I should change the due date to next Tuesday. Okay. Thank you for reminding me. Otherwise, I will see you guys next Wednesday. Have a good weekend. Have a good 3-day weekend. Shout out to MLK for all the things he did. And then I'll see you guys next Wednesday.
Thank you.
Thank you. Have a nice weekend.
Thank you.
Thank you, Mr. Who.
Mr. Who?
Mr. Who, I left, and then I realized I still have a question.
Okay. And I believe Kiara has a question as well. Okay, so go ahead.
Okay. Wait, me?
No, you and Kiara, I believe, both have questions. So go ahead, one of you.
You can go.
Okay, thank you. Wait, so the difference between the tension and pulling force, like in the example where like the horse was like pulling something, that's applied force, not like tension?
It depends if there is a rope or a string and stuff involved. So let's say I have a water bottle and I'm pulling it like this. That's an applied force. If I had a water bottle and like a string, like let's say I have a mask here and I'm pulling it like this. You guys can see my webcam.
Yeah.
Right? If I have like a mask and I'm pulling a water bottle like this would be a tension force.
Okay.
Yeah.
Okay, I got it. Thank you.
Okay. And Kiara, what's your question?
I had a question about it was early in the lecture when the two objects with different mass hit the ground at the same time.
Mm-hmm.
Doesn't I just don't understand how that works, because doesn't one of them have a much bigger force? So wouldn't that just make it hit the ground faster?
So first, as a disclaimer, this is not including air resistance. So this is in a vacuum. So one of them has a much bigger force on them. On the other hand, it also has a much bigger mass on it. So your ratio between your force and the mass are the same. So it's like if I apply a bigger force to a bigger object, right, it's not going to accelerate. The acceleration, it sort of gets canceled out. So even though one object has a much bigger force, it also has a much bigger mass. An object has a much smaller force, but also has a much smaller mass. And the acceleration is the ratio between them. So that's what matters, is the ratio between them. And the way gravity works is that the ratio between them is always the same. This is not true for any other force, only for gravity. Gravity is probably one of the only forces where the ratio is always the same.
Okay, so it doesn't really have anything to do with like velocity or anything like that. It's just the ratio between mass and acceleration.
Mhm, mhm.
Okay, thank you. That makes sense.
Okay.
Bye.